Welcome. Today we shall be learning in this lecture the trace components which are present in the natural gas systems and some of the removal processes. So, first let us see that a number of trace components exist in natural gas which may create processing and product quality and environmental problems if present in high concentration. Even that is why we need to remove them and know about them. So, these are the various types of trace components present in the natural gas, right from hydrogen, oxygen, radon, arsenic, mercury, BTEX and helium. So, this radon is a radioactive material. This is normally radioactive material, whereas BTEX is the benzene, toluene, ethyl benzene and xylene. We shall be taking up helium separately in a separate lecture. So, first we shall see the hydrogen. Now, hydrogen, we know this primary source is the gas streams from the refineries, and hydrogen's levels are rarely sufficiently high to cause any problem. Rather, sometimes the natural gas is added with hydrogen to increase its heating value without posing any accidental hazard, and this is the one use of the hydrogen in the fuel cell. Then we come to the oxygen. Oxygen is as you know that it can be a very reactive gas. So, it is only a contaminant that does not occur naturally, and its best approach treating is this: prevent its introduction into the processing stream, because if it enters the processing stream, it has many hazards, like it can cause, if there is leakage of oxygen through the valves and piping, and there could be oxygen leakage from that. If it is below atmospheric pressure and should be less than 1%. This is a kind of prescribed limit of oxygen in the cell's gas, and these are the some of the bad effects of oxygen. It can causes ignition, and if it reacts with the pipelines, and it can cause corrosion. So, that is why that we find that sometimes the specified limit is less than 1% to about 0.1 volume percent, depending on the particular situation. Now, above 50 ppm oxygen causes these problems. It enhances pipeline corrosion in presence of liquid water. It reacts with amines in gas treating, which ultimately causes the formation of the salt, and if these salts are formed, they can cause scaling problem inside the particular equipment, and it can react with the glycols to form some corrosive acidic compounds, which will be causing the corrosion to the equipment again. It can react with the hydrocarbons during high temperature regeneration of the absorption beds, and then if it reacts, it forms water, and if water is formed, it reduces the regeneration efficiency by causing cooling, because in the regeneration we need high temperature, but water will be subduing the heating effect. That is how it will be reducing the regeneration efficiency, and thereby it will reduce the bed capacity for regeneration. In the low concentration, oxygen is removed by non-regenerative scavengers, for example, hydrazine and ascorbic acid. That means it is low concentration, so they will react irreversibly, and we need not bother to regenerate these particular scavengers. If we are having high concentrations of oxygen, then by catalytic oxidation of the gas stream to produce water, this oxygen is removed, which is then removed in the dehydration step. And we know that gases containing sulfur compounds may poison the oxidation catalysts, and the reduction of the sulfur levels in the gasoline and diesel fuels is needed. So, it is not possible to carry out combustion before gas treating unless gas is H2S free. Otherwise, what will happen? If we do that, then the H2O will be absorbed more on the adsorbents. The oxidizing the process stream after treating generates carbon dioxide, which can freeze out in the cryogenic sections of the plant. So, we have to be cautious that we should not allow the carbon dioxide formation if we are taking the natural gas for liquefaction, otherwise the carbon dioxide can form the solid ice. Oxygen is generally removed from the cells gas along with nitrogen rejection, but this step follows most susceptible to oxygen damage. As we have seen that in the cells gas, the amount of oxygen has to be very small, has to be less than 1% or even 0.1 volume percent. So, that is why in the cells gas we have to remove this oxygen along with the nitrogen. Nitrogen because it reduces the heating value of the natural gas. Next we come to the radon, which is a radioactive material, and its concentration in natural gas is very small, about 10 to the power minus 18 mole fraction, and it does not generally causes health problem because it has a short half life about 3.8 days. And this radon decays into lead 210, then bismuth 210 and polonium 210, and which up to ultimately it goes to a stable lead 206. So, these are the in between radioactive materials which are formed from the radon. The daughter products of radon, which some of which have long half lives, condense on the pipe walls and form a low level radioactive scale which may flake off and collect on the inlet filters. That is why it is important for us to remove radon, so that the intermediate radioactive materials which have a longer life period are not formed and causes this kind of radioactive scaling. And storage vessels can accumulate the daughter products as sludge. Next we come to arsenic. In the arsenic, we know that arsenic pollution in the water at various areas is very critical. So, in similarly arsenic is also there in natural gas. It is a toxic non-volatile solid. That means it will tend to stay in the sludge. It will not be vaporizing along with the natural gas, and it exists in natural gas predominantly as a more volatile trimethyl arsine. That is, this is the formula of the trimethyl arsine, and it usually collects as a fine grade dust, and high concentrations lead to geographically localized. So, that is why we find that there could be some problem with arsenic of the some health problems are caused by the arsenic. It can be removed by some non-regenerative adsorption process. It needs hydration before its removal to prevent the water adsorption, because if water is not removed before arsenic removal, what will happen when it goes through the adsorption column, because arsenic is present in a low amount and water is present at high amount, the adsorbent will be collecting more of the water than arsenic. So, we will not be able to separate the arsenic from the natural gas, and there are several facilities reduce the arsenic concentrations in sweet raw gas from 1000 to less than 1 microgram per cubic meter, and the arsenic must be removed before marketing the gas. Next we come to mercury. Mercury is another hazardous component. It may be present in the elemental form or as organometallic compounds like methyl ethyl mercury, dimethyl mercury, diethyl mercury, or inorganic form like in terms of HgCl2, that is mercury chloride. Now, elemental mercury distributes itself between the both gas and the liquid. Mercury has very low vapor pressure, about 3 into 10 to the minus 7 bar at 0 degree centigrade, but vapor phase concentrations are order of magnitude higher because of the non-ideal behavior of mercury at operating conditions. So, at 0 degree it has a very low vapor pressure, but at operating conditions, which is a very high temperature, the vapor pressure is quite substantial. So, it needs to be removed. Now, most operators want to remove this mercury to the extent that it cannot be detected by the available analytical techniques. So, there is no particular level up to which mercury has to be removed, but it depends on the how much capable we are capable to detect the mercury. If we cannot detect it by some available analytical methods, then we assume that we are safe. and the concentration of mercury is to be 1 parts per trillion by volume. PPT is 1 parts per trillion by volume, that is about 0.01 microgram per normal cubic meter of the gas. And these are some of the hazards caused by the mercury. We know that it is hazardous for the human. Then mercury causes catalyst deactivation in the downstream hydrocarbon processing, so it has to be removed, and it forms amalgam with aluminum, and as per this aluminum is generally used in the cryogenic heat exchangers. So if amalgam is formed, then what will happen? It will weaken the material of construction of the heat exchanger, and if the material is weakened, then what we will find that there could be gas leakage or even catastrophic failure. It causes environmental and safety hazards, and if mercury is ingested, goes into our system, then there will permanently damages the brain and the kidney. So mercury has to be removed. It is removed by adsorption, and it is complete removal of mercury requires reduction of the mercury compounds into elemental mercury. So we have to convert all the compounds of mercury into the elemental mercury to ensure its complete removal, and generally these processes use chemisorption for removal and to remove also the organic mercury compounds through physical absorption. So both chemical adsorption and physical adsorption are used for the removal of the mercury, and during this removal of mercury, some of the arsenic and lead also get removed. And these are the two types of adsorbent process for mercury removal. One is non-regenerative and regenerative, and we find that for the non-regenerative processes, that means in this case we are not regenerating the adsorbent, and it can happen that if we are not going for regeneration, then the process becomes simple, and there is a high installation cost is there, the pressure drop is high, and the disposal cost is also high. On the other hand, this regenerative process is in the other way, it has a lower pressure drop and no additional equipment cost, and it can remove both mercury and the water and in the dehydrator, and it is generally practiced simultaneously with some regenerative adsorption applications such as drying. That means both for dehydration and this mercury removal are done simultaneously, and we may need a secondary mercury removal treatment for the spent regeneration gas. Next we come to BTEX. In the BTEX we have the benzene, toluene, ethyl benzene and the xylene. So this is concentrates both in the glycols, that is used in the dehydration of natural gas, and amines, which is used in the natural gas sweetening because of their low vapor pressure at the flash conditions and their affinity towards glycol. So BTEX hazards are that they are environmentally concerns are that BTEX if present they are in the volatile organic compounds. So if they go into the air, so that will be causing many problems, and this benzene is considered to be carcinogenic, that means it can cause cancer, and it is also considered to be toxic to the air, and the emission limits for the air toxics are lower than that for the volatile organic compounds. So that is why these BTEX have to be removed. They are more lethal than the volatile organic compounds, and these BTEX can also get frozen in the cryogenic plants, and if they freeze, then what will happen? They will cause plugging problems in the various cryogenic equipment and the pipelines. So that is why these BTEX have to be removed. And for removal, what we do, sometimes we adjust the plant operating conditions so that to minimize the quantity of BTEX in the glycol absorber. Then the gas is incinerated, and by incineration of the BTEX we get the carbon dioxide and water, and sometimes this BTEX is condensed and recovered as BTEX liquid, and which is also sold out for making other chemicals. So that is how we are able to remove the BTEX from the natural gas. BTEX can also be removed by using the carbon adsorbents, and amine absorption is also done to remove the BTEX. And if in case we are absorbing the BTEX, then both acid gas and BTEX are stripped in the regenerator and traditionally vented if the H2S level is low, or sent to Claus if the H2S level is high for the sulfur recovery. These are the references for more detail on these trace components. Thank you.